Good morning, everyone. Welcome back to class. I hope midterm 2 went well for everybody. We'll talk about results once we get them in a little bit later. The quick look at the scores. If you recall, I predicted scores would drop for midterm 2, and that seems to be the case. The average is probably going to be about 8 to 10% lower than midterm 1. Didn't have to be that way, but that's what it is. It does commonly happen. Like I said, chapters 3 and 4 are harder in nature than chapters 1 and 2. We also have the nature of being a college student. I think we can see lecture attendance is slowly dropping. I'm glad you guys are here, so I appreciate your attendance. Sometimes exam week leads to a little bit of complacency that week. We got to keep moving. All of our classes do this, where we got to keep moving through exam week and keep learning new things. So you guys know this, you're here. I don't have to tell you that. But for those listening to this 2 or 3 weeks from now, would have been good to listen to this 2 or 3 weeks ago. So try to keep caught up with your classes, your notes, your homeworks on a lecture-to-lecture basis, and then hopefully come exam time, we're not putting everything together the weekend before the exam. So anyways, we're in chapter 5 here. We were talking about this on Monday, getting into the nature of chemical energy, the first law of thermodynamics, that energy is not created or destroyed. We were getting into enthalpy, so that's kind of where we're going to be picking up today, is talking about enthalpy. Go. And so then we'll be getting into enthalpies of reaction today. So what we'd like to do is try to understand that if you have a reaction take place, we'd like to understand like what's the delta H of the reaction, what's the enthalpy change. Then we'd also like to try to get through the idea that enthalpy is kind of like the energy change, or it's related to what we might think is the delta E of the reaction, that this is going to be very much approximately equal to delta E. In some cases, almost exactly equal to the energy change we're thinking between A versus B. And this gets us into the thinking, is our reaction where A is here and then B is here in terms of our relative enthalpy or energy. And so this diagram here would be showing B is more stable. That would have a negative delta H. And so that means heat would be given off by this reaction. And then we also could have the alternative reaction where A is here, and then B, the products are higher in enthalpy. And then that would be the case where our delta H was greater than 0, a positive value. And it can turn out to be the case, and we'll see an example in a few moments, that reactions can spontaneously take place that absorb heat from the surroundings and look like this case here. And we also have reactions that give heat off and look like this case here. Now we call this exothermic when heat's given off by the reaction, when the heat releases reaction, when the products are more stable, lower in energy, lower in enthalpy, that we call that a release of heat. That's exothermic. And then the case over here, that would be endothermic, where the products have to absorb heat in order to form from the reactants. And so reactions can be exothermic or endothermic and still take place. Now, we'll learn later in chapter 19, or whoever you take them 20 with, if you keep taking chemistry, that being exothermic is in a way better towards making the reaction occur spontaneously, but there is an entropy effect that we're not talking about in this chapter. So if you want to really know if a reaction will actually occur or not occur, you have to know what delta G is. You might remember this equation, that delta G is equal to delta H minus T times delta S. This is a very important equation. This comes up in chapter 19. Delta G is the one. If it's negative, the reaction should occur. If it's positive, the reaction won't occur without external forces. And so that comes up later. So you may have this in the back of your mind. Does delta H determine if the reaction occurs spontaneously? No, it's not the delta H that really matters towards spontaneity. It's delta G, though delta H being negative is helpful towards making delta G negative. So anyways, getting into some of the things that we were talking about on Monday, we were trying to get into the sign conventions for things like heat, work, and energy change for a process. And so we're introducing the equation that delta E is equal to Q plus W. And I like to throw these tags on, like the delta E of a reaction is equal to the heat change of the reaction plus the work change of the reaction. Just so that we're thinking of the change of the energy with the perspective of the reaction. We're going to then have the thought, as we get into this chapter, of when a reaction loses heat, where does it go? It goes to the surroundings. So if we have the A up here, the B's lower in energy. So if we're thinking of the case where A goes to B, like this, and we know our delta H is less than 0, this is going to look like the delta E is being given off by the reaction as well. So the energy in this reaction in this example is releasing energy. And so if the reaction releases energy, that's negative. If the reaction has to absorb energy, that would be positive. If the reaction releases heat, and that's what this reaction here looks like it's doing, is it's releasing heat through the process of the reaction. And so if heat's released, that's negative for the reaction because the reaction loses heat. Where does the heat go? It goes to the surroundings. So the heat lost by a reaction, so the Q reaction is equal to the negative Q, the heat change of the surroundings. So if the heat is lost by the reaction, it's gained by the surroundings. And then if you have the opposite case where if heat has to be absorbed by the reaction, this would be the A here, B up higher, the endothermic case, that's going to look like where heat has to be absorbed by a reaction. And so that's a Q sign of positive relative to the reaction. So heat has to be absorbed by the reaction. Where does it come from? The surroundings. And so if the reaction is taking place in a flask, the flask should get colder because heat's being lost by the solution. Heat's being lost by whatever the solvent is in order for the reaction to take place. And then the W sign, if the reaction's pushing something, if it's causing something to go into motion, that's causing a loss of work by the reaction through its speeding up of something else. So you can think we're going to have fast molecules push into something, so the molecules in the reaction have to slow down, so they're losing work as the thing that they're pushing into gains its speed and it gains the energy of motion. So it gains the force times the distance it's moving, it gains that energy through work. And so the reaction loses work to cause objects to go into motion. And then the opposite would be if the surroundings are accelerating inward onto the reaction and causing the reaction to either speed up or to contract, then that's W being positive. And so this looks like expansion. So this is, why is this not working? Expansion. And then the positive, this would look like contraction. So a reaction occurs and we drive a piston upward, would be expansion, that's working on the surroundings. And then if we have a piston moving, say, inward onto the reaction, that would be contraction. That would be an example of work being positive. Now, it's harder to pick the sign up. You can't just look at the sign of delta H and know what the sign of W is. W is more related to how the reaction is being used. It's more important, if you ask me, for like a mechanical system. And we're really trying to understand chemical systems in this chapter. So this is a chemistry class, not really a mechanical engineering class. But if you had a car engine, then a car engine is going to be doing a lot of this work here. But of course, you could have a hybrid car that's recharging a battery, and that's going to be on this side over here. So mechanical objects work as a bigger percentage of the energy change. What we're going to try to do, and we're going to see this pretty early here today, is try to look at enthalpy in a particular system doesn't allow work to be done, and allows us to look at the heat change and know that it's exactly equal to what we call the enthalpy change. So let's get onward towards that kind of discussion here of what enthalpy and delta H are and how we can calculate and understand what the enthalpy change is for a process. And so just know that whenever, and I like to make sure I show for enthalpy, like a delta is always thinking like an A to B, always some reactant to some product. The change in enthalpy is the delta H. You can imagine that this would be equal to whatever the enthalpy of B is minus the enthalpy of A, that would be my delta H. So the delta is just the final minus the initial. Now, if we then said, well, let's look at one of these enthalpies, how's it defined from physics, let's say, is that the enthalpy is the energy change plus the pressure and the volume if the substance is a gas, or just related to the pressure times the volume of the substance. And so this is the connection between enthalpy, energy, and then some fundamental relationships or properties of the substance. And so then you can think of taking a delta H, so take the change in H, that would be the delta before and after the energy plus the PV. So this is kind of like saying it's like the energy plus the pressure times volume of B, and then minus the energy plus the pressure times volume of A, that would be like our delta for calculating our delta H. And so then we can then write this, just moving the delta sign through the pressure times the volume. Now, something happens for a particular system. We were getting into systems at the end of class last time, and the three main systems that we encounter that we call chemical systems are either an open container, an open system, which is just a container open to the atmosphere. And that container, we call that a constant pressure container. So this is just an open system, which is a very common container. So it's a container that's not sealed in. And the other two types of systems that really don't come up all that often until maybe one example, like a little bit later in the notes, which is a closed system where you just put a lid on the system and then don't allow the pressure, you don't allow the volume then to change if you seal the container in, and the pressure could change. So we'll see constant volume systems a little bit later, very briefly. But most of the examples we see are open systems, open containers that have a constant pressure. And so pressure is constant, pressure can't change, so we write pressure, then the change in volume. And we could talk a little bit about how certain reactions can cause a change in volume depending if a gas is created or consumed. I don't think it's worth going into that much of a discussion here, but the idea would be that if you're creating a gas during a reaction, so if you look at the reactants versus the products, and the products, if they have more gas, that's going to lead to expansion. That's good for having work happen. So the expansion of the gas could be what drives work to take place if we have like a piston to drive. And then if we have gas being consumed during the reaction, we have then the contraction. So loss of gas will cause then a contraction. But the key would be we'd have to have some sort of a piston or some sort of closed system to drive that to take place. If we don't have a closed system, then there's nothing for a gas created or consumed to be pressing upon. So we're always acting against atmospheric pressure and keeping a constant pressure. And we can also recall that work had this fundamental relationship. There was a slide where we showed that work just turned out to be equal to negative. I'll rewrite it here since my writing's covering it up. And this should be a V. And so work is equal to negative pressure times volume. And so if we just remember that work is negative pressure times volume, we can sort of look here and see that I can sub work in here would be negative work though. So delta H would be delta E then minus work, because the plus P times delta V is just negative of work. And so my enthalpy is the energy change minus work. And then I can also recall, well, remember delta E is Q plus W. So if delta E is Q plus W, so I can sub Q plus W in here. And what happens? Well, you have delta H is equal to Q. And then we put the little symbol P in just to mean constant pressure. So it's the heat change of constant pressure. And then plus W minus W. So work cancels itself out. Now, I like to think of it this way, because I think a simpler explanation for why work disappears in the equation is that there's no way that the reaction can do work. There's nothing to press upon. So if the reaction is at constant pressure, it's just impossible for that system to do work. And so the energy change in the reaction is just all going to be in the form of heat exchange. And so the simplification, the reducing of the heat change to being the only energy change that's possible, meaning there's no work being done by the process at all. So all of the energy change is heat, and then we call that heat change the delta H. And so the delta H, I think the H comes from heat, is why we use the symbol H there. It's the heat change. So we often call delta H the heat of reaction. So it's the heat change that the reaction undergoes. And so if you look at delta H being the heat change, now sometimes I prefer, and I wish the book would just call it Q reaction, and then maybe the symbol P, just to clue you in that it's the heat change, the Q change of the chemical reaction taking place. And this leads you back to the kind of case where you can have delta H be less than 0, and that looks like this, where A is higher, B is lower in terms of their relative enthalpies. And then if you have the case where delta H is greater than 0, then that looks like the case we were talking about earlier in the slides. So it looks like where B is going higher in enthalpy than A, so heat has to be absorbed when it's positive and delta H is positive, and then heat's given off when delta H is negative. And so delta H is just our heat change. And so exothermic, again, that's this one here, so that's our exothermic, and then this is our endothermic where heat has to be absorbed. Okay, so delta H reaction is the heat gained or lost at constant pressure, and we often call delta H just the heat of reaction. So you can call it the enthalpy of reaction too. That's probably a better term because it is the enthalpy of reaction, but the enthalpy of reaction is the heat change of that reaction at constant pressure. And then even if we seal this reaction in, if we want to think about the sealed reaction, it's very, very closely equal to the heat change of the constant volume, the heat change of constant volume. And so when we get to the point where we close in a system, we actually see that work is so small, we'll ignore it anyways. You know, so we either, within the two most common chemical systems being the open system or the closed system, that for those two systems, work is either negligible, so much that it disappears in the constant pressure, and it's very, very small if we even look at the constant volume system. If you then go to a mechanical system, obviously not going to be the case, but we're not, like I said, a mechanical engineering class. This is a chemistry class. We're trying to understand our key chemical systems. If you recall, there was a third chemical system we mentioned, which was the isolated system, which is where you had a sealed container, then in an insulated environment. You might be thinking about then the area outside of that insulated environment is completely unchanged by what's inside. The isolated system is pretty much space filler. It's not really a system that's of too much importance to anything we talk about in this class. But just to reintroduce or remind you that there were actually three systems: the open, the closed, and then the isolated. It's the open and the closed that I really want us to think most about, because the open container constant pressure is the one we encounter the most in lab examples, and then the sealed in example is very closely related, where our delta H. So if we look at our delta H for a Q reaction at constant volume, you just put a little approximate sign, that the Q reaction is approximately equal to delta H for the constant volume system, that they're very similar to each other. Okay, so let's look at a couple examples here of reactions. So, I was mentioning earlier that exo versus endothermic, like the nature if a reaction is exothermic or endothermic doesn't tell you if the reaction should or shouldn't take place. If we look at two examples here, calcium chloride solid, this is going into water. So imagine it dissolving into water, and it should ionize because it's one of our soluble ionic compounds from our solubility rules. And so this compound should dissolve in water. Its delta H is negative, so it releases heat during the reaction. And then ammonium nitrate, again, another compound from nomenclature that we know, or not nomenclature, another compound that we know from chapter 4 and solubility rules that should dissolve in water because it's an ionic compound. That's water soluble, so all ammonium salts are water soluble, and we should get ionization to the plus and minus ions of it, and it turns out to have a positive delta H, so that heat has to be absorbed for this reaction to take place. And let's just keep reminding ourselves that the positive here is endothermic, and this one here is exothermic in terms of the signs. And so let's take a look at these reactions here and try to see, maybe even come up with a prediction. So if I throw a thermometer probe into a water bath, or just a flask containing water, it's probably going to be about 20 degrees. It's a little bit colder. It's like 19.8 degrees right now. So I have calcium chloride, and I have ammonium nitrate. And so if I had calcium chloride in water, do you think the water is going to get hotter or colder as I add it in? What do you guys think? Temperature go up? Who says it should go up? Who says it should go down? Well, let's see. And so, again, remember the reaction's releasing heat. Okay. So calcium chloride, delta H is negative. like I could pass this around as a pack, but I feel like we're not supposed to pass chemicals around in class. So we could theoretically make a hot pack out of this. It's 35 degrees right now. The temperature is going up. So why is the temperature going up? So we add this to water. So we add the calcium chloride to water, and we see that the temperature of the solution is increasing. So we're making a solution when we add the compound to water. The thing we're tracking the temperature of is obviously not just the calcium chloride. We're tracking the temperature of what the calcium chloride is in contact with from the before versus the after. So we're really touching the surroundings of the reaction. So when we measure the temperature, I'm measuring the temperature of the surroundings temperature is increasing. Well, why is that? Well, think about the reaction. The reaction is releasing heat. The reaction loses heat. It doesn't mean that the temperature would drop in the water because the water is obtaining heat. So the water is the surroundings here, or the solution that is forming is the surroundings, and the Q of the surroundings is greater than 0. Why is it greater than 0? Well, the Q reaction is the negative sign of the surroundings. So if the reaction loses heat, then the surroundings gains the heat. So if this is less than 0, wrong sign, if this is less than 0, then this must be greater than 0. So the heat lost by the reaction is given to the solution that is allowing the reaction to take place, and therefore the reaction's getting hotter. And so, like even I just kind of misspoke. The reaction's not what's getting hotter. The surroundings, what's in contact with the reactants versus the products, the water that's watching this reaction take place and helping it take place, that's what's obtaining the heat. That's what's increasing. And so if I touch the flask, then I'm part of the surroundings, and then I'm going to feel that heat that's going to be given off by this reaction. So right now it's at, well, it's cooling back down because we have this other flask that's temperature, so it's cooling back down. So I'm back to about 30 degrees already. So now let's test the opposite case here. So let's test where we take ammonium nitrate. And again, my water here, it's about 20 degrees again, so it's taking it a moment or two to drop down. And so now, what do you think happens if I take the compound that has a positive delta H and dissolve some of it in the water? It should drop in temperature, right? And so, I'll add some ammonium nitrate, stir a little bit. This is really cold already. It's already 5 degrees, 4 degrees. And so I can certainly feel the temperature. That's 74 degrees, right? Yeah. And so it's actually negative. For a moment it was negative anyways. And so we were getting really close to the freezing point of water just by adding that compound of water that has the positive delta H. And so we can create a hot pack with something that, if it dissolves in water, has a negative delta H, so that negative delta H, the energy released by the reaction, can go into the water. And then this compound, we add it to water, the temperature of the solution drops because the heat from the solution is going into that reaction as it takes place. And so the ammonium nitrate has to absorb heat for that reaction to take place. We know the reaction takes place from solubility rules. And so what's going on here is our Q reaction has to absorb heat. The Q of the surroundings has to lose. Okay, so picking up from here. So the Q surroundings, the Q reaction is, so the reaction is absorbing energy, absorbing heat. The surroundings has to be losing heat. And so the surroundings is losing heat. What happens to its temperature? Temperature has to drop. And so temperature is just proportional to heat. We add heat to something, temperature goes up. We take heat away, temperature drops. So we're taking heat away from the surroundings of the reaction here. When the Q reaction is positive, Q of the surroundings is negative. So the surroundings here, the water's losing heat. Okay, so the sort of lesson here is that we can have reactions that have delta H's that are positive or negative, and the reactions can still take place spontaneously. Both these reactions occurred without any external forces. The calcium chloride, if you see some solid left behind, just hasn't, and some of the ammonium nitrate too, they haven't totally dissolved yet, but a lot of the compounds did dissolve. And so we hit the solubility, we probably saturated the two solutions with as much of those two compounds as we could get to dissolve in that amount of water that we had, and we were seeing a pretty big temperature change. So we're getting up to about 40 degrees for the calcium chloride and pretty close to 0 for the ammonium nitrate. So we're seeing that delta H can be either sign, and the reaction can still be spontaneous, and we're also then seeing exothermic releases, heat gets hotter, and the endothermic reaction occurring is causing the temperature to drop. And if we start thinking about this, when we want to calculate delta H, like we'll do this probably not today, maybe into Friday's class where we try to track and study enthalpy changes, or how do we find experimentally a delta H. What we're gonna do is we're gonna carefully figure out how much water do we have, carefully figure out how much compound actually dissolves in the water, and from that information, and if we do it in an insulated beaker that doesn't lose heat to the surroundings very easily, like a coffee cup, something that's insulated, then we can maybe track the temperature change of the solution and try to figure out what the delta H of the compound is. So we're going to see a little bit later that if we're sort of careful with the experiment we just did, we could probably determine the delta H of an unknown compound. But the thought would be, if I put an unknown compound into water and the temperature goes up, then the delta H is negative. If I put an unknown compound into water, the water temperature drops, then I know the delta H is positive. And so we can also talk about state functions a little bit. This comes up in this chapter. What a state function is it's a path-independent function. And so delta H and delta E are path-independent, meaning if you go from A to C and then from C to B, that energy change, like let's say, you know, the A to C path is plus 20 for the delta H. So it goes upward by 20, and let's say C to B is minus 40. And so C to B goes down by 40. And so then you know that if you add these up, C cancels and A to B, because we're summing up these reactions, that A to B should be minus 20 kilojoules. And if that's not true, then we're violating like the first law of thermodynamics. This also becomes a Hess's law example that we'll see a little bit later in the chapter by name, but if we can add reactions up, we can just add up their delta H's, and from A to B, the delta H should be minus 20. And so it doesn't matter if you go A direct to B should be minus 20. If you go to A to C, C to B, the net result should be A to B is minus 20. You could go A to C, C to D, D to E, E to B. All of those need to sum up to minus 20. So it doesn't matter the path you take from A to B, the difference of energy between A and B should always be minus 20. This is kind of like if you said the distance between here and Cleveland, some specific point is 122 miles, let's say. That's true no matter what path you take. That you can go from here to here, here to there, you can go to Toledo to wrap around to Erie and then to Cleveland. The distance between here and Cleveland is still 122 miles. The total distance you will have traveled depends on your path. So the path you take, your total distance traveled would depend on that distance, but still the 2 points are still separated by whatever their distance is. And so that's what delta H and delta E are. Delta H and delta E are kind of like A versus B. What's their difference of energy? No matter what path you take to get there, A to B still has that difference in energy. So then heat and work, though, those are path dependent. So we can take a reaction such as the energy stored in a battery. We can take the energy stored in a battery and just have a set of coils that we heat up where we get most of the stored energy out of the battery in the form of heat. And so almost all the energy comes out then as Q. Very little work being done. The only work being done is the work it takes to push the electrons around to make that happen. And so work is very small in that case. Or we could use the energy to power a fan. The fan will get a little bit warm. The motor, the fan will warm up a little bit. So there is some heat that's involved here, but much more work to move the fan. And so you can think, how much heat versus work can a reaction do? There is a fundamental limit by how much energy difference there is in the battery that's stored. We have a stored battery, so we have high energy. We use up the battery, goes to lower energy. So we have that stored energy that can be given off. All is heat, all is work, or some combination of the two. So the amount of heat versus work you get out of a reaction depends on how you use the reaction. And so the heat versus work are path dependent. They depend on the path and how we're using, so those are non-state functions. And so things that are non-state functions would be things like heat versus work in a reaction, and then like the total distance traveled to get from point A to point B is also path dependent. The actual distance between the 2 points is path independent. Like the delta H and the delta E are path independent. Now, the delta E does determine the magnitude of heat versus work. So delta E does limit you for the heat versus work a reaction can do, but it's like saying if delta E is minus 10, then you can be minus 9 or minus 1, or you can be minus 8 or minus 2. You could be minus 7 or minus 3. So the sum of the two is limited by delta E, but the magnitude of the heat versus the work itself can be anything that a process allows it to be. Okay, let's get into a couple questions here. So HCl is added to water, hydrochloric acid. Well, HCl is hydrogen chloride in the gas form. You add it to water. We know it's going to dissolve to form H plus and Cl minus because HCl is a strong acid. But so then if we add this to water, the temperature of the solution rises. So does that mean that the reaction is exothermic or endothermic? And what's the sign of delta H for that reaction? What do you guys think? Exothermic or endothermic? Who says endothermic? Anybody say endothermic? The water bottle does. No, it's exothermic, of course. So delta H here should be less than 0. It should be an exothermic reaction because heat's being released by the reaction. That's why the temperature of the solution goes up. So the temperature of the surroundings rises because the heat of the surroundings is increasing. The only way that this can happen is that the heat of the reaction drops. So whatever the sign is for the heat of the surroundings, it's the opposite for the reaction. So if the reaction is, if the surroundings is going up in temperature, it's going up in heat, therefore the reaction is losing heat to cause that to take place. And then this is the meaning of delta H. So delta H is the heat change of the reaction. And so if the Q reaction is less than 0, then so is the delta H sign. So a solution of gold chloride absorbs hydrogen gas to form HCl and gold. This looks like an example of a redox reaction. And so this would look like AuCl3 plus HCl forms gold solid, and then H2 gas. If we want to balance this out, I could go 2 here, but then I can't really balance my I swapped the reactant. This should be H2 over here. So gold chloride in solution absorbs H2 gas, and then the product here is HCl. If I put a 2 here, then I can't balance my chlorides because I need at least 3 chlorides. And so if I put 3 here to balance the chlorides, then I would need a 3/2 here. So let's not do a 3/2, let's do a 3, let's do a 2, a 6, and then a 2. So the 3 times 2 is 6, 6 times 1 is 6, so that's 6 hydrogens, 6 chlorides. Anyways, just making sure we have the right balancing of the reaction here. But a solution of gold chloride, this is the reaction that's taking place. And so the temperature of the solution increases as this reaction takes place. What's the sign of Q and W? So let's think about these signs here. So the temperature of the solution increases. That's telling us something about delta H and Q. So the temperature of the solution increases. Then we have the heat of the surroundings is increasing. So the heat of the reaction is decreasing. So less than 0 for our delta H and for our Q. Now work here, this is coming from our gas is being consumed by the reaction. So when we see here that HCl is an AQ, gold's a solid, a gas is being consumed is going to lead to contraction. We're consuming a gas. Let me rewrite the word consume since I'm being too sloppy. So we're consuming gas during the reaction. We're losing gas molecules. That's going to lead the surroundings, the contracting inward onto the reaction. If we think of the opposite, if we create a gas, if more gas is present on the product side, then we're going to be pushing into the surroundings. Pushing into the surroundings should be work that is negative. That's the same. So if you push the surroundings away, same as heating the surroundings up. And so both of those are negative in sign. So this is work moving inward onto the reaction. And so that's work being positive. And this is in the perspective of the reaction. Just remember, heat, you can think of what's the heat change of the reaction versus the surroundings. So I like to make sure that we say Q. Are we talking about the heat of the reaction or the heat of the surroundings? The heat of the reaction is negative because the heat of the surroundings was positive. I mentioned this before, last time I haven't said this phrase today. You can't put a thermometer on a reaction. You can only put a thermometer on what the reaction's in contact with before and after the reaction. So the only thing you can really put a thermometer on is the surroundings. So if we say the temperature goes up or down, it's always the surroundings. So the temperature here, the solution, that's the surroundings. That's what we can put a thermometer on, not the reaction itself. So we have to imply what had to go on with the reaction relative to the surroundings from their relationship, that the Q reaction's negative Q surroundings. Okay, so the sign of Q here should be, so the Q reaction's less than 0, heat's being released by the reaction, and then work's being absorbed inward by the reaction. And so W is positive, so we should have negative for Q, positive for W. Now, what about delta E? Delta E is a little tricky because we'd have to know the sum of a negative and a positive number. And so sometimes we'll know delta E's sign, sometimes we don't. This is a case where we wouldn't know the sign of delta E. Presumably it's negative if the reaction is taking place, but sometimes that's not, delta E can be positive or negative, even if a reaction is taking place spontaneously. So we want to sum up the Q and the W. And only if we know both of the signs are positive or negative do we know the sign of delta E. And so if I know Q is negative and W is positive in sign, delta E could be negative or positive. I don't know. So delta E, if we were asked for its sign here, the answer would be we don't have enough information to determine the sign of delta E, because it's a sum of a negative and a positive number. We don't know which one's bigger than the other without having actual data. Now, you can probably presume that W is pretty small from what we were talking about earlier, that there's not much work change going on with the change of gas particles, so work's probably a small component. If the heat change is the large magnitude, probably going to win out. But again, if you're asked for the delta E sign, we can't determine it from this data here in this question. So let's get at some more like practical examples of using enthalpy. So if you ask me, the first three sections of chapter 5 are conceptually hard to understand, but what we hope you gain and understand is the sign conventions on delta E, Q, and W. I hope we've done good enough examples. There's more in the daily quizzes and in the homework if you need more examples of those sign conventions. We hope that you understand that enthalpy is the heat change. And then what we want to do now is like get into looking at some different type of reactions, how we can understand how to manipulate reactions and get their delta H's, and then how we can study and determine some delta H's through calorimetry, and then how we can put together some other ideas for manipulating reactions or determining things like heats of formation as we get towards the end of the chapter. And so let's look at delta H here with this term, that delta H is an extensive property. Delta H, if you notice, when I write like A to B, in my general example, and I say that, for example, the delta H is minus 20. Let's go back to this example here. That notice that there's no per mole. That the mole is assumed to be 1 mole of A forming 1 mole of B. So the moles are assumed to be whatever the coefficients are that I wrote them onto the reaction. So the assumption here So we're assuming 1 mole of A completely turns into 1 mole of B. So we're assuming 100% yield of that reaction. We're assuming that the coefficients in the reactions are moles, and the energy change for that quantity of reaction would be minus 20 for A to B. Now, if I said you had 2A goes to 2B, now the implication would be we have 2 moles of A going to 2 moles of B. So if I double the quantity of the reactants, what should I do to the delta H? I should double it. So delta H here should be equal to minus 40 kilojoules. And the implication is because I have twice as much. So if 1 mole of A gives off 20 kilojoules of energy when it converts to B, if I have 2 moles of A, it should give off 40 kilojoules as it converts to B. So what that means is delta H is an extensive property. It's quantity dependent. So it depends on the quantity. It's extensive in the sense that every reaction has its own delta H too. So each reaction does have a characteristic delta H. So each reaction will have a characteristic or different delta H, but then that delta H is dependent on the amount. And so that's why if we look at water, liquid to gas, let's say that the delta H of that's plus 40 kilojoules. Let's think about this for a minute too, of liquid water boiling. Do you think that that should be exothermic or endothermic? Just in terms of how we think of the terms being applied. Should liquid water have to absorb heat or give heat off to boil? It has to absorb heat. That's why we put it on the stove. So we put it on the stove, so we give it heat so that it increases its enthalpy. So the delta H sign should be positive for a boiling. If you then had a freezing, if you took liquid water to solid water, so to freeze ice, we have to take heat away, so that should be exothermic. And so anyway, so we have liquid water going to gaseous water. If the delta H for that process is 44 kilojoules, that's 44 kilojoules for 1 mole of water, turning into 1 mole of water vapor. And then if we do the opposite, or if we do the thing we did for A to B, double the coefficient, so we have 2 moles of liquid water converting to 2 moles of gaseous water, the sign of delta H doubles. So we now go to 88 kilojoules. So if you double the coefficients, you're doubling delta H. If you made it half a mole of water goes to half a mole of water vapor, that would be 22 kilojoules. So you can cut coefficients in half too. So cut these coefficients in half. Delta H should be 22. Now, if you flip the sign, if you took water vapor and want to condense it into liquid water, then you have to flip the sign. If you didn't just flip the sign here, we'd be violating the laws of thermodynamics. We'd be creating or destroying energy. So if it takes 44 to boil water, we get 44 kilojoules back when we can recondense the water. So the energy it takes to go up is exactly equal to the energy we get when we come back down. And so that's minus 44 kilojoules for gaseous water turning into liquid water. And the delta H is dependent on the physical states of our reactants and products. So if we're writing a combustion reaction of methane, let's say, for example, so methane combusts, we know with O2 to form CO2 and water. We balance it out here to form water as a liquid. And let's say that that reaction has a delta H of minus 890 kilojoules. And this is just a quantity of the reaction. We'll see a few different ways we can determine that number from maybe information in like an appendix of our textbook. But that's what the delta H of the reaction is equal to. If we then said, well, the enthalpy it takes liquid water to convert to gaseous water is 88 kilojoules, you see how 2 liquid water cancels on both sides of our reaction. If I add these reactions up, then the liquid water canceling itself out. So I then end up with gaseous water as my product. And because I add the reactions up, I should be able to sum up the delta H's. So I should be able to take minus 890 plus 88. That goes to minus 802 kilojoules for forming water as a gas. So we have to pay attention to the physical states of our reactants. There's an appendix in the back matter of your textbook that lists the standard enthalpies of formation. We'll talk about that as a topic later. But if you look up the standard enthalpies of formation of different substances, you could look up all the reactants and products. And if you sum up the products, you can then subtract the reactants. But the key is, if you go to the appendix to look these things up, you got to pay attention to physical state. You got to make sure if you're looking for water gas, you grab the water gas and not the water liquid, because they have different values. Okay, so let's say we have this problem here. So is heat released or absorbed And how much? So when 5 grams of hydrogen peroxide, H2O2, decomposes at constant pressure according to this reaction. So this reaction has a negative delta H. That means it's exothermic. Is heat released by the reaction or is it absorbed by the reaction? So heat's released by the reaction. Where does it go? To the surroundings. So heat released from the reaction to the surroundings. So heat here should be released by this reaction. Now how can I calculate how much heat's released? So if I want to calculate Q reaction, now in a way Q reaction and delta H, if you recall, delta H at constant pressure is equal to the Q reaction at constant pressure. Now let me mention that a lot of times when I write Q reaction, I'm usually thinking for a random amount of reactants, I usually think Q reaction. For a balanced reaction, I usually think delta H. Even though they're equal to each other, and you could theoretically sub the two in, like you could say Q reaction is equal to minus 196 kilojoules, but it's more common we have a balanced out reaction that we say that's delta H. And if I then say when 5 grams reacts, what's the heat change of that reaction, which is in a way delta H as well, but just symbolically I usually say Q reaction for a limiting amount of the reaction, like 5 grams of the hydrogen peroxide reacting. According to the reaction, for every 2 moles of H2O2 that reacts, the heat change of the reaction is minus 196 kilojoules. Like this is a fundamental conversion factor I can write using the balanced chemical equation. Because this equation is saying when 2 moles of H2O2 reacts to form 2 moles of water and a mole of O2, that the delta H of that reaction is minus 196 kilojoules. So what I'm looking at here is this coefficient, and then that's moles of that substance versus the Q reaction, or the delta H minus 196 kilojoules. So when this much of the reactant reacts, this is the heat of the reaction that the react. So that's the heat by which the reaction is losing heat. So what I need to do is convert H2O2 to moles. And so that conversion, it's like 34.02, right? So it's 1.008 times 2 plus 32.00. So that's 34.02 grams per mole of H2O2. And I'm converting that so I can use this conversion factor here of for every 2 moles of H2O2 that reacts, the Q reaction is minus 196 kilojoules. But this too is easy to miss. It's really easy to do this conversion to moles of H2O2, then just multiply by 196. We have to divide that for every 2 moles of H2O2 that reacts. So you go 5, divide by 34.02, times 196 negative, divide by 2. So I'm just keeping this sign along for now. I'm going to reinterpret it here in a minute. So I get 14.4 kilojoules. From the grams canceled, the mole cancels. And so that's the heat change of the reaction. The Q reaction is negative 14.4 kilojoules. Now, I like to think of Q reaction kind of like we might think of money. You know, like if you go to the casino, and I know you went to the casino, or if you go on these betting apps to bet on football games, nobody says, what's your money change for the weekend? They say, did you win or lose? You know, so when you think of money, it's usually in a positive sense. Usually like I won $20 or I lost $20. It's never like my delta money change was negative 20. So you said that to somebody, they'd be like, wait, what? Heat is often this way too. So we like to think of what was not necessarily, we tend not to ask the question, what's the heat change of the reaction? We tend to ask the question, was heat gained or lost by the reaction? And then where did it go? And so the heat here was lost by the reaction. So 14.4 kilojoules of heat is lost by the reaction. And of course, that means it's released. And of course, that heat goes to the surroundings. So where does it go? It goes to the surroundings. So the answer to this question, like if we ask this question was, calculate the heat release, it would be 14.4. Now it's a positive number, right? Because it's like that's the amount of heat that was lost. So Q reaction is negative 14.4, and then the meaning of that is 14.4 kilojoules of heat was lost by the reaction, and that's equal to the quantity gained by the surroundings. So you can think here the Q surroundings, heat the surroundings gains, plus 14.4 kilojoules. So a lot of times in this chapter, the heat change is a positive quantity. We intentionally make it a positive quantity. The idea of the heat was lost, the negative sign of heat is what the word lost is implying. So if the reaction gained heat, then it would have came from the surroundings. So if this reaction were endothermic instead of exothermic, we would have said that the quantity of heat that was changed to the reaction was the amount of heat that was absorbed by the reaction. Okay, let's take a look at another example of a reaction here. And so this one here has, I'll write the reaction up in a minute, but I have barium hydroxide, BaOH2, and then I'm going to add to this some ammonium nitrate. And what I'm going to try to do, like both of these are solids, but this is barium hydroxide that has a little bit of moisture absorbed into it. You can't really tell per se, but it's like crystals of barium hydroxide that have water molecules absorbed into it. And so it's called a hydrate salt when you do that. And so then this is just the same type of ammonium nitrate as used earlier. And so I'm supposed to put all this in here. Also supposed to put a little water here on this piece here. So what should happen when I mix is that a reaction is going to take place, and this should freeze the water, make it really, really cold for the water that's with the barium hydroxide, and then cold enough so that I can freeze that piece. Geez, it stinks. I can freeze that piece of cardboard to the flask. And so the whole idea here is can I make the flask cold enough so that it freezes over? So I'm going to give that another moment to do that. Let me show you the reaction that's taking place here. Is that we have barium hydroxide reacting with the ammonium cations and ammonium nitrate, and then we're producing the acid-base reaction between the hydroxide ion and the ammonium cations. So we're taking an H plus off of the ammonium, giving it to the OH minuses to form water. So we're forming two water molecules, and then we're forming two ammonia gas molecules that are flying away. That's what I was kind of smelling being given off by the reaction when I said it smelled. And then the byproduct here would be barium nitrate. And so that's a reaction that's taking place. The delta H here, presumably, is greater than 0 because the temperature of the surroundings is getting colder. Now, can we see, like, I can feel it getting colder on my hand. Let me see if we've been able to freeze. So I was able to freeze that piece of cardboard from the fact that this is cold. So you can come up and feel it's cold, but it has a bad odor, so I don't recommend it. But you could feel the temperature being colder as well in the flask. You can sort of prove that we can freeze, a piece of cardboard to the flask. Okay, so that's one last example of an endothermic reaction. And then just to show you, we'll be getting into how we study and determine these delta H's on Friday through calorimetry. All right, guys, I'll do it for today. I'll see you next time.